Hello, everyone. I'm in the spot where I'm in between your flight and your workshop, so I'll try to keep it short and try to keep it interesting. So let's see how it goes. So these are our experiences with NVMe Fabrics, and my slides are in largely four sections. I'm going to give you an overview of the NVMe Fabrics first, followed by some of the examples, then the Linux implementation, the open source implementation of the initiator and the target, and the performance numbers, comparing them, and micro enhancements that we have been doing, and lastly on how to debug it. So let's start with it. As we are in a storage section of the workshop, most of us are aware that we have NVDIMM and NVMe over PCIe and our traditional SAS and SATA drives. So if you look at the stack, we have at least 2 to 3x gain. I'm sure these are the old numbers, and the last two weeks numbers would be even more in terms of the number of the IOPS gain and the latency improvements that we see. So how the traditional storage arrays, the enterprise class arrays which are built, that provides various different features of the data, availability, resiliency, redundancy, snapshots, and so on. So the CPU looks really a small block, but it's the most smart software that's running there doing all this work. So you have your server or an array facing NIC or HBA, then you have a CPU running smart software, and on the backside you have a huge storage cluster or storage devices that's providing you all the workload to address it. So traditionally you have SAS and SATA, and the better way to go forward with it is to have replace that, quite a lot of that, with the NVMe or PCIe-based storage, where you have the PCIe fabric instead of the SAS or SATA fabric, which is limited to 12 or maybe 24 Gbps, versus PCIe fabric that lets you expand to 24 to 48 drives and much higher performance. This is an interesting graph where the market projections about how the NVMe or the PCIe drives going to be into the enterprise market. We have seen a lot of enterprise picking up the NVMe, but the last 2 weeks announcements are really astonishing to me. So I was able to hire and rent and use NVMe drive in one of the most prominent cloud at a cheaper price than the price I used to travel from my home to this conference. It was at 15 cents for an hour. We get 100K IOPS NVMe drive at very normal price, which is 15 cents, and 400 GB. So that's the kind of market adoption of the NVMe drive today available in enterprise as well as in the cloud. And that's why NVMe Fabrics plays a very vital role in having those drives accessible from the remote to the initiator node. Tom in his presentation very clearly highlighted how and why we need to have a remote access, because data without copies in enterprise is almost like a RAM. It's not available. I totally agree with it, and we'll see how NVMe Fabrics fills that gap. So there are various modes in which NVMe Fabrics can work. This is about NVMe Fabric standard is available from 2016. Implementation is available in Linux and many other OSs. It works today over RDMA, Rocky V1, V2, InfiniBand, and iWarp. These are some of the last year or a few months back demos at 2 different conferences from various different storage vendors and the OS side. I'm not going to go over to the names, but they are very visible. These are the real products in market today available, and not just demos, which are also at least 6 months old, available for use. So done with the what NVMe Fabrics and is available. Now let's go in little deeper of how the stacks and what are the different pieces of the software that's being available. So NVMe Fabrics is primarily for block storage, bypasses all the SCSI layer, and takes all the benefit of the multi-queue. So if you look at the stack diagram, you have NVMe Fabric target at the bottom and the traditional SCSI stack. And on the upper side is what you see is the initiator side. So RDMA stack right away fits, NVMe stack fits right at the same level as where the iSCSI or the SCSI stack fits in. And that allows us to bypass and make the use of the fast NVMe devices, cutting down quite a lot of layers into the software stack. So why RDMA and NVMe is a perfect fit? Very simple reasons. Both the protocols are asynchronous, both are queue-based, and all the queue semantics matches them with each other very nicely. NVMe has an admin queue, IO queues, and RDMA has similarly send queue, receive queues, and completion queues. Send queue and receive queue matches up to the NVMe's IO queue and admin queue, and the completion queue matches up with the receive queue, so that all the NVMe completions can come into the receive queue. And as we go down at the layers, the mapping is pretty straightforward, and that brings the simplicity. The simple the software we have, it's very likely that you will get the best performance out of it. So RDMA obviously achieves buffer to buffer copy from one node to the other node, and NVMe makes the right use of it. So if we see in the rightmost side, you have NVMe submission queue that maps to the RDMA send queue, and on the target side, it maps to the RDMA receive queue. So 64-byte NVMe command sits in there. It comes to the other side on the target, and the target software puts that from RDMA receive queue to the NVMe's NVMe's send queue, and that's how the I/O flows through four of this queue, out of which there's only one physical queue at the target side. And similarly, the path for the completion is just exactly reverse, where the completion flows into the RDMA send queue, coming back to the initiator side into a RDMA receive queue, and the I/O completes. This is about the NVMe working group. These are the member companies from all areas, from storage, CPU, networking has contributed towards the standard, and it's in progress. 1.3 spec is very soon, I believe, to be out, but before that, the NVMe Fabric spec is very much in use today. So shifting now to the performance and the Linux implementation before that. So the host side code is implemented in a very standard way, where we have a Fabric driver, PCIe driver, and the common code. And similarly, the target side follows the same model. Both is a kernel implementation, open source. Target side is configurable through the config.fs. So all this NVMe semantics that we have, subsystem, namespaces, controllers, and the host, all of them is modeled and that can be configured through the config.fs, including the ACLs, that which host can see which subsystem is available, but not up to the namespace level. On host side, we have three transports available to be usable. RDMA, including all the variants of RDMA, fiber channel, and then we have a loop transport as well to test and see the performance through the Fabric common piece of software. On the host side, all of this is accessible through the NVMe CLI. NVMe CLI works across PCIe as well as the Fabric for discovery, connection establishment, or discovering the namespace, as well as disconnecting them. One of the critical point of NVMe implementation is a multi-queue implementation, where there is one queue per CPU through which the NVMe commands being flowing through. And shortly we will see how it performs compared to the iSCSI or ISER implementation. So this is pretty much I've covered where how the queues are being mapped. One good benefits of RDMA is all the block layer SGs mapped to the RDMA SG through a fast memory fast registering the memory regions. So every block SG can map to one or more RDMA SGs, and through memory regions, the data is being shared from target to initiator side. So this is a high-level stack block diagram. Let's see all the major components out of it and how the stack is being organized. So it's actually upward down, thinking from the storage or from the target side point of view. What you have in the at the bottom is the NVMe core layer, and below which is your initiator drivers. So let's start from the top. Let me try. So you have an RDMA target driver, which is just generic target driver. Any new transport can be supported. And on top of that, we have RDMA target driver or an FC target driver. They both link to the common driver. And all the common drivers talk to the block storage stack, which is important thing to notice. What it means that the NVMe target driver can take benefit of any of the block storage available onto the system, which means it could be an NVMe drive, or it could be a standard SATA drives, or it could be traditional rotating media, or it could be a device mapper based storage devices. And so therefore, the abstraction is very well done, where the NVMe Fabric target can talk to any backend device and not just the NVMe device. Of course, NVMe device is supported. And when you use the multi-queue NVMe devices, you can see the performance benefit out of it. Now that block storage stack further down talks to the NVMe core, which is usually on your initiator side. But this is a complete picture on where you can see how the data flows. So the bottom is your NVMe core layer, which has an Fabric driver. NVMe core layer is again generic, agnostic to any Fabric, including PCI. It directly talks to the PCI because that's the native interface. And underneath, it goes to the Fabric host driver so that any other Fabrics that needs to be extended can be further extended down. And NVMe CLI is a user space interface. Again, write abstraction talks to the NVMe core, not bypassing any layers, and configures the right parameters that it needs to do to to the right fabric. So usually you will see, if you are an initiator side, you will just see the bottom part of it, and target side would see actually all of them, because when it's talking to an NVMe device, you will see a whole flow from target to the PCIe device. What it means is you could actually chain some of the NVMe devices through an RDMA fabric onto the backend side, especially when you are running hyperconverged infrastructure or a DM layer where you could be writing to a remote disk from your initiator. So that gives you a lot of flexibility when you build a standard storage array or a hyperconverged storage array. This is another slide that talks about the Linux code organization. So if you see the major code on the target side, common code is 39%, which is roughly majority of the common code across all the fabrics. And the RDMA's code is really small, which is 20% out of this on the target side. And you'll see the similar numbers on the host side. So this is a great abstraction that's been done. And that's how we see how the NVMe and RDMA layer and their queuing model fits so well together, because of which we are able to abstract most of the code out into the fabric layer. So I'm going to go talk over some of the micro benchmarks that we have done. Some are useful, some are more theoretical, but it highlights some of the critical point around the latency and the IOPS that it can deliver. So this was the setup that we used, 100 GB ConnectX-4, 64 GB RAM, both initiator target side. And we used both null driver as well as the real NVMe device. But the performance numbers are around the null driver so that we can see how the latency plays a vital role from the fabric side. So we always run 70-30 OLTP side kind of workload to make sure that one or the other does not impact the other one. So the performance charts are for the mixed workload. So there are three graphs here. One is not actually visible at all. The one which is not visible or very less visible is NVMe Fabrics. This is the latency chart. Lower is obviously better for latency. The tallest graph that you see is iSCSI over TCP. The red one that we see here is an ICER iSCSI over RDMA. And the shortest one is NVMe over Fabrics with the null driver. And the performance difference are visible. We pick a number for 4K IOPS. The latency is 5 microseconds end-to-end between two hosts from application to application, which is 184 microseconds, which is evident that if you put, from the Tom slides, if you have seen an NVDIMM device can deliver 6 microsecond latency, and other two fabrics does not obviously fit well to deliver that latency. And that's why the NVMe Fabrics is one of the key ingredient if you want to build a storage array, either in your front end or in the back end. So the interest question is why? Why is it that it gives such a low latency? The two major parameters that play a role is the mapping of the NVMe commands with the RDMA commands is one. The second one is the multi-queue implementation. When we are on a 64 cores, the multi-queue implementation of the NVMe stack delivers such a low latency number where there is no need of a contention across the CPUs fighting for the queues and the locks. So this is one of the key latency parameter to consider. This is just another chart for the IOPS. So So latency and IOPS goes obviously well together. You can still achieve the IOPS if you want to achieve with the ISER or iSCSI, but that would require us to scale large number of logical units to get that scale. Even with that scale, we probably can achieve the IOPS, but not the latency that we have seen in the previous graph. So if I do not have the absolute numbers here, I wish I would have. All right, so in the previous graph, this is the absolute latency number. For 4K IOPS, we are at 5 microsecond. If you have noticed, the latency from 4 to 8 has doubled to 18 microsecond. Right? That was not the case until 4K. So let's see. This is for mixed workload. Majority is right here. Similar graph here on the IOPS. If you see the latency, the IOPS, even with NVMe, has dropped from 2 million IOPS to 790K IOPS. And why? So we did the micro enhancements. There were 2 micro enhancements being done. NVMe write commands can complete within just two operations. It supports the inline data, probably close to the MPI words and eager data, where send and the actual data can go in one command as a RDMA send operation to the other side, and the target can complete with RDMA send operation with a 16-byte CQE with 1. Until 4K, the target exposes the inline data size as 4K, and we were able to achieve the 2 million IOPS because of the 2 operations. If you do with the block write operations, that involves memory registration, memory invalidation, and the regular send and completion operations. So there are 4 operations on the send side for either for read commands or for commands beyond 4K of size. And that was one of the primary reasons why we don't see, why we see such a large drop in the IOPS. So it might sound that IOPS is hypothetical, 790 or 2 million IOPS for one device. The best we have seen is around 500K write IOPS that the latest Intel Optron or the other drives can do. But when we build an enterprise class storage array, there is not going to be one device. There is always software or hardware RAID involved, or the replication is involved, and therefore you will always see multiple devices. So 790K is a very practical number to see here, and there is always scope for us to improve upon it. So we improved. We improved on that with two micro enhancements. We increased the inline data size from 4K to 16K. Many of the PowerPC can go up to 64K because of the default page size being 64K. But that's not enough on the target side. On the host side, discovered that the number of SGs being used to perform the inline send operation was just 2. Because some devices does not support more than 2. 16 SGs is very common on the send side. And instead of 2, we increase it to 3 SGs for the send side, include plus 1 SG for the 64-byte command. And these are the good numbers that we see with this. So of course, this is a memory versus IOPS or latency trade-off. But this is very much desired. So the current patches that's been posted is a static configuration, and we've received a valid comment that we would like to have it on a configurable parameter through the config.fs. So the next patches would like to address that. So when you have then the storage array can do a smart things where it can reduce the inline size up to 0 to 64K, depending on how good the backend storage being exposed for the host side. So if you see here, this is a relative chart. So the 700K IOPS is now 1300K IOPS, and the latency for the mixed workload. The important point to consider is the mixed workload, that the latency of the write is also affecting the read latency. So the read latency is reduced because of these two factors. One is finishing the write faster, which are there in the queue. And the second one is the memory registration and the invalidation has been reduced. And that's another area to see how that can be improved, even for 8K or higher when we don't want to use inline. So if you see for 8K or 16K, we see almost 100% plus, more than 100% latency reduction, and so the IOPS. So these are the patch in progress that hopefully should be in kernel soon. And moving on to the last part of the NVMe Fabrics experience, we received plenty of requests and inputs on how to debug this. There are various set of peoples and not just developers who need to understand, because this is a 6-8 months old protocol, how things work, what subsystem, what's controller, how it is exposed. So an obvious thing is to have somebody look at the protocol traces and find out what's going on, because everyone is not developer who debugs this system, tests this system. So the obvious choice is to have open source support. So in open source, Wireshark has now support for NVMe over Fabrics, and most of the commands of NVMe native commands as well as the Fabric commands both can be traced now, that can be looked upon. This is a sample that I have captured from my developer build. Is that a connect command? It's a Fabric command which has NSG data, and you can see it is for an IOQ1 into the trace. So all the connection management commands as well as Fabrics commands are processed. In this slide, you will see the read and write commands can also be processed now, including the latency. So you can see and search and parse commands which has taken more latency in which LBA range, that can tell you that which LBAs were on a different storage, or you had a cache miss, or any other thing that you might want to debug in your setup. So this should be available anytime in a Wireshark release sometime in June. Until then, it's all developer builds that we have to make use of. That's all I have for our experiences.
Hi. Is there any support for discovery service in the stack?
That's right. So discovery service is inbuilt today into the target side as well as the initiator. On target, you can configure controller as a discovery controller through a well-known subsystem name, and one or more subsystems can be discovered through that.
Okay, and I noticed your mapping. I mean, I guess the straightforward mapping is like QP to submission queue, completion queue to QP and things. Is it possible on target side to use SRQ instead, or it's not?
So SRQ is already in place. SRQ support is part of the upstream today, and it's a module parameter. You can set module parameter to make use of the SRQ. I personally don't recommend to use SRQ right now, because the performance test I ran, the performance degrades drastically with SRQ when we use. So all the commands are going to one SRQ for a given initiator, and there is a lot of contention around it. So one of the input from Sagi was to have a per CPU SRQ, and so with that multiple initiators, can direct the command to each of this SRQ into that CPU. And once we have that, the performance should match up to what we have without SRQ.
Okay, and did you say that for the multi-queue support that it's sort of bound, to however many CPUs you have or something like that? It's automatic, or this is a...
It's automatic. So the initiator side code discovers how many of the online CPUs are there, and there is one RDMA or NVMe queue, or the multi-queue is being created for each of the CPU. It's all automatic.
Right.
There are options where if you want to reduce the number of queues through a discovery command, we can still do that through NVMe CLI.
Right. Well, and so for I guess you didn't show, do you have some CPU figures for all this great IOPS and things?
I don't have a CPU figure, but I mean, I have, but I haven't presenting. So in all of the performance tests of the micro benchmarks that we improved, and without that, the CPU utilization is less than 20% on a 64 CPU system.
Okay.
With the 2 million IOPS for all 512 to up to 8K range.
Okay, and at this point, do they implement the like authentication commands, things like that?
So authentication commands are in place in Fabrics. They are already there. But which authentication scheme is being used is not part of the scope right now, or probably I'm not aware of it. But there are authentication commands. So whenever the queue connection is being established, right after that, the first command that has to go out is an authentication command, which is in place. But if you have to correlate that with the iSCSI chap, probably it's not there up to that.
Okay. All right. Thank you.
Just wanted to give a couple of comments. You had asked about things like SRQ and stuff, and I just wanted to make the point that one of the design goals of the NVMe over Fabrics driver was to code it over, kernel mode verbs, but such that it could be run over any type of device, not just InfiniBand, right? So, and it indeed does. It's been tested over InfiniBand and Rocky and iWarp and OmniPath, right?
Right.
So.
Yeah, so SRQ is one of the optional feature, and it's left as an optional to make use of.
So they make it as a module parameter, so like if you have that capability in your fabric, you can use it, but if you don't have to, right? Well, yeah, I don't know exactly which features are in, iWarp versus
right. So
stuff.
SRQ would be helpful in saving the memory of the system, especially with the inline when we want to do higher inline size. SRQ would help greatly improve the memory utilization, especially when the workload is not aware of whether it's going to be read intensive, right, or mixed of them. And in that case, the Sagi's point to have a per CPU SRQ would be a great addition. Yes.
Okay, so in your when you showed those Wireshark traces, how are those Wireshark traces captured? Did you use IB dump or just capture from mirror port, or?
So there are two ways it can be captured. In one case, I have used a Mellanox OFED, which allows to trace the traffic for the Rocky. I captured for Rocky V2, but you can capture through IB dump as well for InfiniBand. I capture for Rocky V2 in two ways. One is through Mellanox OFED, where I can use the standard TCP dump to capture them. And in second case, I captured through a soft Rocky stack, which is much easier to capture on a live setup.
Okay, thanks.
Thank you.